course is of course solid state physics, and this is the starting lecture on 5.3, our treatment of the free electron model. So what we will do here in the upcoming lecture is that we will start by general introduction to the section 5.3 that focuses on the free electron model. So essentially, we are now still assuming that our potential function in the Schrödinger equation is 0. And then in the actual 5.3.1 section, we will calculate the quantum mechanical eigenstates of our system. And here, of course, like I said, we are really considering only a freely moving electron. We don't have a zero, we have a zero potential function in our treatment, and we will find out that what will be the dispersion relation of our system. We will find out what is a so-called Fermi energy or the Fermi level of the system. So how we populate the n states with our n electrons. And then we will discover what is the electronic density of states for the free electron model. And we end up discussing the importance of the system's temperature on the actual Fermi level. And we will distinguish between the Fermi energy and the Fermi level, since in some texts the distinction is being made quite clear between the Fermi energy and the Fermi level. I'm myself not that picky on this, but since there is a difference between the energy and level of the Fermi energy, then maybe I should try to point to you that there is this difference in the terminology. And then we end with the lecture in giving the kind of general occupation probabilities of these electron states in our system. So we will speak how the Fermi-Dirac statistics change when we go to the finite temperatures. So this is what we will learn in this lecture. And like I promised, I will start with a general introduction to our section. So we will now, in the upcoming 4 lectures, we will introduce to you the free electron model. And this is also known as the Drude-Sommerfeld model. So it's essentially a quantum mechanically correct classical Drude model, where we are considering that a metal consists of freely moving conduction electrons, and the properties of the metal are being dictated by this movement of conduction electrons. And what we will do in the next chapter 5.4 or section is that we will then generalize this treatment to nearly free electrons. So then we will have a periodic potential function in there that is not 0 anymore. But in this 5.3 section, what we will do is that we will start by having this lecture where we will be solving the quantum mechanical problem of a free electron, so no potential. We will find out what are the energy eigenstates, and then we will populate these energy eigenstates with our electrons. And then in the next lecture, we will calculate the electronic heat capacities, because if we can know what kind of energy states we have, we know how they are being populated, then we can also calculate what are the associated electronic heat capacities of such solids. And then in the follow-up lecture, we will very briefly introduce to you the Wiedemann-Franz law, which was a nice experimental discovery that relates the thermal conductivities of materials with electrical conductivities, especially of metals. And then finally, we will discuss of screening of the electric field that takes place in a piece of a metal and to a degree in a piece of a semiconductor. And this final lecture, in a way, it validates us or explains us why this free electron model and the nearly free electron model are so good as models by just based on the kind of assumption that doesn't seem to make sense, that we can assume that the conduction electrons are free, so that they don't see the positively charged electric nuclei, the ionic cores that are nearby. So that the final lecture then explains how come this seeming discrepancy in our treatment is actually not bad at all. So it kind of motivates our assumption of freely moving electrons. So please bear with me all the way to the final lecture on our section 5.3. And now we go to the actual lecture that I want to give to you in this lecture, is that we start discussing the quantum mechanical eigenstates. So we will solve the quantum mechanical problem at hand, and we will get the eigenstates for our system, and then we will populate our system with the n electrons that we have. And in this treatment that we have here, our quantum mechanical problem is that we have a free single electron, and it's in a box, so that we are treating essentially a potential U equals 0, and that will be our free particle based implication. So that it's a free particle, it doesn't feel any potential, so it can't freely move. And we assume that it's in a box, so that we have a periodic matter, and the kind of periodicity of our cubic solid. For simplicity, we consider a cubic solid. Of course, it could be a little bit differently sized material, but the kind of like end conclusions don't really change. So for simplicity, we just consider a cubic solid and not a strange parallelogram shaped three-dimensional structure. The length of a solid cube will be L, and of course then the subsequent volume V will be L cubed. And this is our periodic boundary conditions, and then the wave function that is associated with our electron in this periodic system must comply with the lattice periodic function restriction. So the psi in a position of R, so in Cartesian basis in a x, y, and z position, this must be equal to the wave function psi in a position of x plus this L, the length of our piece of a cubic solid we are treating, plus y and z. And similarly, of course, when we go to this lattice constant of L to a distance of y, so we go to the y coordinate of y plus L, this must be the same kind of wave function as we have in the original y position. And finally, for the z direction, we have the same thing, so that we kind of complete our assumption of periodic boundary conditions. So that this is the kind of box in which the electron is. And of course, we know the solution into this problem already. We have solved it before, and we know that the wave functions is essentially like the wave functions are essentially plane waves that are normalized, and they propagate in a direction defined by their wave vector k. So this is hopefully a familiar psi wave function to you already. And this is what follows when we have a zero potential function. So the electron wave functions, they're just simple plane waves inside a material. And that sounds like quite a bit of a freely moving particle to us, like a plane wave propagating in a given direction, happily with a whatever speed it propagates. So the periodic boundary conditions, what they do is that they, in essence, they discretize the energy states, and they discretize also the wave vector directions into which our electron can go. So k in a Cartesian basis can be, of course, described by its components kx, ky, and kz. And here, because of the periodic boundary conditions, this k wave vector is being discretized. So it can only get very specific values that are 2 pi nx divided by L, and nx, ny, and nz are the integers that describe the state and the energy of our system. If you're really into mathematics, please denote or witness that these integers nx and ny and nz, they actually form an ordered set of integers. So somebody could say that they form a tree tuple. And then, for example, when we are summing over states, we would be summing over this kind of entity of a tree tuple. But essentially, what it is, it just means that it's an ordered set, and set means that these three numbers, they come together because they are associated with a given state, a given wave function, given plane wave describing an electron that is propagating in a given direction, and then these ends, they also define the energy of our system, and why they are being ordered, so that it really matters in which direction we have the integers. So nx is really nx, and it can be totally different value than ny and nz, so that the order cannot be changed of these integers. So it just forms an ordered set. Nothing fancy, but maybe the piece of mathematical terminology here sounds intimidating, but it's not. Just become familiar with it, and then it becomes pretty understandable. So now we have wave functions, psi i's, and these are essentially our eigenstates, eigenvectors, and they are associated with very specific energies, ei's, and these will be our eigenvalues of the problem. So we have an eigenvalue problem at hand where we have the eigenvectors, the eigenstates are our wave functions, and then the eigenvalues are our eigenenergies of the system. And essentially the energies that now depend on the k, the amplitude of the k, are of the form that we have the reduced Planck's constant h bar squared times the amplitude of the wave vector k squared divided by the 2 times me, where me is the mass of our electron. And of course, the amplitude of the k, like we can describe that using the kx, ky, and kz, because in essence, it's the length of our wave vector k. So h bar, it's of course h divided by 2 pi, meaning that it's the reduced Planck constant, reduced as in slightly smaller in value than the actual Planck constant h, and me is the electron mass. So this is the kind of like a memory rule I used myself. So why on earth is it being called a reduced Planck constant? Well, it's smaller in size than the original Planck constant. I hope that they helps in case you don't already remember it by heart, like what is the difference between the Planck constant and the reduced Planck constant. So as the name suggests, essentially, that's how the memory rule goes. And then we have the energy eigenstates, energy eigenstates for a given nx. And let's just change the nx from minus 15 to 15 in the figure, and the ny, nz, and ny and nz are equal to 0. So that we see what kind of possible energy states we have as a function of nx, or in principle as a function of kx, of course scaled. So we see that the kind of states, they form first of all a discrete states. So it's not really a continuum of states. And then also we see that when we go to a higher n values, the energies increase, and it seems to form a parabola when ny and nz are 0. And of course, like all of these can be non-zero, so then things become a little bit more complicated if you would really need to sum up over these states, as we will do in the upcoming lecture. And now we have essentially the dispersion relation. So we have the energies E described as a function of our wave function K. So essentially as a function of nx, ny, and nz. And let's now like estimate that how densely they are being populated in the K space. So how close by the different energy states are. And we know that a single energy value is every energy value are equally close to each other here, so that each of these energy values fills a space of h bar squared divided by 2 times me times 2 pi over L squared. And if the periodicity of our system is this L is roughly of the order of 1 angstrom, and this is roughly the case when we're dealing with solids, the lattice constants are usually of the order of angstrom. Like for a diamond, if I recall it correctly, it's a 0.357 angstroms, so 357 picometers. So that this when we plug that in, this L value into this above equation, we see that the states are very densely spaced indeed. So very, very close by. And what we will do next, because we want to treat a solid that actually consists of many atoms and subsequently of many electrons, we must now populate many states with these electrons. And basically we can do that by just recalling that the electrons, they are spin half fermions, and then we just take use of the Pauli exclusion principle. And we have 2 spin states, so that in essence, we must go to a kind of energy states that are higher in energy than the ground state. So essentially we have n over 2 different energy states to fill. Because energy-wise, the different spin states are degenerate in this treatment of ours. So that the spin doesn't yet play any role in our treatment. Besides the fact that we don't need to go as high in the energy states, because we can fill 2 electrons into a given energy state. Spin up and spin down. So, the states are equidistant and they are very closely spaced. This is what we learned. And now we want to kind of understand how we could estimate what is the level of highest energy state what we reach when we form the solid. And this highest state essentially lies on a surface of a sphere of a radius in max or k max. So this is what we want to find out, that where this highest energy state lies. And we can calculate this by just forming an equality that is of the form that the number of energy states, n over 2, must now fit inside on a sphere of 4 over 3 times pi times n max cubed. So essentially, like inside a sphere, we must have an equality of n divided by 2 must be equal to this size of the sphere. And this equation we can solve for in max, and in max, when we solve that for, we get an equation that n max must be equal to, inside the parentheses, 3 times capital N, the number of states, per 8 pi, and then we take the cube root of this. And this is essentially the kind of like highest integer or nx squared plus ny squared plus nz squared, and this inside the square root that the system will be in. So we can now use this and we can really calculate the highest energy level that we have that is being populated by electrons when we are at a 0 Kelvin temperature. And maybe you already remember, but this level of highest energy is known as the Fermi energy, EF. And in our case that we're dealing with a free electron. We have the Fermi energy level at 0 kelvins to be h bar squared times k max squared divided by 2 times the mass of an electron, me. So in essence, when we plug in what we just discovered for the k max, we have the h bar squared divided by 2m, and then inside the parentheses 2 pi over L squared times n max squared. So this is our Fermi energy, EF, at a 0 Kelvin. In practice, we know for metals that the Fermi energy, EF, is around few electron volts. So this is roughly kind of a good rule of thumb to remember. That this is how much of energy is being associated with the electron at the Fermi energy. And now remember, we are dealing with the free electrons. So in all of 5.3, we are focusing on a case that the potential is 0. And then what this Fermi energy EF really means, that it is the highest kinetic energy that we have associated with a single electron. And that electron is present in the solid. And please remember, we are speaking of the Fermi energy, so we're dealing with a 0 Kelvin temperature. So this is the ideal case that we don't have any thermal energy in the system. And please remember that if we would speak of Fermi level, then that would be the highest kinetic energy associated with the electron present in the solid at a given finite temperature. So not at 0 Kelvin anymore, but at some kind of finite temperature. Let's say 50 Kelvin or at room temperature, whatever. But not at 0 kelvins. That's restricted for Fermi energy. Please distinguish this point in the terminology, that there actually is a difference between a Fermi energy and a Fermi level, even though not all the references and probably our booklet does not really distinguish this difference between the Fermi energy and the level. They're almost the same, but not exactly. And what we will do next is that we want to calculate the electronic density of states, so that when we're done, we could really start plugging things into the usual equation describing the heat capacity of a material, and so that we could follow that line and estimate what is the electronic heat capacity of a metal. So we will next calculate the electronic density of states, so DOS, and this we label here as a G, and it is a function of energy. And of course, it's being defined similarly as the density of states for the phonons. So G, the electronic density of states, is being defined that it's the derivative of the number of electrons or states with respect to the energy. And please remember that density of states for phonons, D, was being defined similarly. So we just took the derivative of the number of phonons with respect to the frequency. So to speak, with respect to the energy. And this definition for the density of states really suggests that what we should do next is that we should really find a relation for our electron that then gives us the number of electron states n as a function of energy, because then we can plug that into our definition, and then we can really estimate what is the density of states. And we do this by basically rewriting the earlier equation. So the earlier equation for the Fermi energy, and that gives us the energy as a function of n. So that will be equal to h bar squared divided by 2 times the mass of an electron me, and then inside the parentheses we have 3 times pi squared times the capital N number of states in our volume we are treating, so L cubed, and then this is into the power of 3/2. And this, of course, we can solve with respect to n, and that would give us what we are seeking here. I don't show it how it's being solved, this equation, but of course, like we all know how to do it. The end result is that we have the volume of space, V, divided by 3 times pi squared, and then inside the square parentheses we have 2 times mass of an electron me times the energy divided by h bar squared, and then this to the power of 3/2. And this, of course, gives us tools to calculate the electronic density of states, G. So by definition, the G is the derivative of n with respect to E, and now we have an equation for n, so we can, of course, do the derivative, and what we have at the end of the calculation, we have that the density of states is V/2 pi times 2 times me divided by h bar squared to the power of 3/2 times the square root of energy. So please remember this functional form. The electronic density of states for a free electron has a square root dependence on energy. We will be seeing this many times in the upcoming figures and in the upcoming equations. And this is a very important quantity, so please consider at least remembering some of it. And if you remember some of it, please remember that we have the square root dependence on the energy. That's a very good starting point to kind of remember that whenever we are using this, is that what comes out due to the fact that its functional form is as above. So at the 0 kelvins, the above density of states gives us exactly what is the population of our all electron states. We remember we are assuming single electron approximation here, and this is nice and fine. What we must do before we are ready is that we must consider also the possibility that our system is at a non-zero temperature, so at a finite temperature where we are actually like dealing with, for example, room temperature or 100 kelvins or something in between or something above. And then we know that we should really apply the Fermi-Dirac statistics to the problem at hand, and that would then give us tools to calculate what is the final electron occupancy. What is the probability of an electron to be in a given energy state? So in essence, what happens when we are in a finite temperature is that some states are being thermally excited at a given time to an energy state that is above the Fermi level. So in essence, to an energy that is higher than EF. And then at some point, the other electrons that are in a higher stage, they will be relaxing at the same time. So it's really a dynamic system where states are being excited due to a presence of thermal energy, and at the same time, the electrons that are in a higher energy, they will be relaxing into these lower energy states due to the fact that they actually can minimize the system's energy that way. And please remember the Fermi-Dirac distribution that gives us these statistical tools to estimate what happens nearby the Fermi level. The Fermi-Dirac distribution E as a function of energy and temperature is being given as a 1 over exponent E minus mu. Mu is the chemical potential divided by kBT. Kb is the Boltzmann constant, and T is the temperature plus 1, since we're dealing with fermions here. So here, Kb is the Boltzmann constant, and mu is the chemical potential. So essentially here, instead of using the Fermi level, we're using a slightly more generic or general property of our solid here, mu the chemical potential, so that they also other different properties than just the temperature, and they kind of density of states can matter, like where the electrons are. So for example, if we would have an external voltage, then the chemical potential would be changed. Or if the system would be in a slightly different environment, the chemical potential would be changed. And somehow, I'm not an expert on solid state physics, but somehow this use of chemical potential it makes this treatment more general than using the Fermi level, concept of Fermi level. But here, we could just use EF here, but for sake of generality, we're instead using the chemical potential. So that they're very, very similar in nature, these quantities. And how do we calculate this chemical potential mu or Fermi level? In essence here is that we can take use of the normalization condition that we have for our system. So we know that in total we have n states, and then when we integrate from 0 to infinitely high energy values, the density of states G with the Fermi-Dirac distribution. And when we calculate, we must come up with exactly the number of states that we have. So in essence, when we take use of the density of states and the Fermi-Dirac distribution, and integrate over them with respect to the energy, the outcome of the integral must be that we will have just the number of electron states that we have in our system. So essentially, we require that the electrons must be in some state. And now I will end the lecture by showing a hopefully clarifying figure that shows what happens in our treatment or how it has happened so far. So we started with the density of state for a 0 Kelvin temperature. And the usual Fermi level for metals is of the order of several electron volts. So this is now the kind of strict boundary, a very, very discrete boundary, the Fermi energy at a 0 Kelvin temperature. So here, the Fermi level is really a discrete line. Either the electrons are being populated into these energy states, or they are not being populated at all. And here, this darker blue curve, this is our square root of energy functional form for the density of states. Here we have the Fermi-Dirac distribution, and then we are dealing with a finite temperature. So nearby the Fermi level, we actually have a kind of blurriness in the Fermi-Dirac distribution due to the fact that there's, of course, a non-zero possibility that a given energy state, a given electron state is being excited due to the presence of thermal energy into a higher energy state. And the width of this blurriness in the Fermi-Dirac distribution is of the order of 4 times kBT. And when we are in a room temperature at 300 kelvins, this blurriness, the width of it is around 100 milli-electron volts. And that's, of course, very tiny compared to the Fermi level of several EVs. So in essence, this is very narrow, but we did this region of Fermi level with respect to the whole density of states. So basically what I'm trying to say here is that these pictures are not very, very carefully made, and that the most of the electrons are not nearby the Fermi level at all, but most of the electrons are really here and not that much electrons are in here in this border nearby the Fermi level. And then the final picture here is that we have the density of occupied states. So we are multiplying the density of states G with the Fermi-Dirac distribution, and we are ending up with this density of occupied states. And at a finite temperature, we see that there's this blurriness taking place nearby the Fermi level. So the middle one is the Fermi-Dirac distribution. Do not forget that. And please remember that this width of the Fermi level is very narrow compared to the actual Fermi energy associated with the metal. So the electrons, of course, are inside the blue area, so that's where they are. And at a 0 Kelvin temperature, the Fermi energy is a very, very discrete line. So there's a sharp boundary between the case of electron states being populated, so that there really is an electron. And when we go to the higher energies, there's no electron at all. So this is what I wanted to say to you in the first part. And I will stop here. And in the next lecture, we will now use this developed math in order to estimate the electronic contribution to the heat capacities of solids. And then we will also discover a little bit of the discrepancy between the classical Trude model and the Dulong-Petit estimate for heat capacities. But more on these later in the upcoming lecture. So I thank you for listening, and please join me with the next lectures that we will be discussing next. Thanks and bye-bye.